Okay, let's get started. Everyone turn in your quiz 6. Going once, going twice. Sold. Okay, thank you. So the Mother Nature got to us on Friday, so thankfully she didn't get us this time. So we have actually quite a bit to do today. I don't have your homework 1s graded yet because I had some research stuff I needed to do that was due Friday, and I didn't have time to grade everything. So I'll try to get everything done by Wednesday. Any questions since last time? Okay, so let's actually think about where we are at this point. So what have we done so far? Yeah, so DFAs, so we talked about DFAs, and then we talked about, as a generalization of that, what else did we talk about? NFAs. So we did NFAs, and then we did what? Regular expressions, and we saw that we can convert between any one of these two, right? So if you have one of the three, you can always make any one of the other two. So if you have a regex, you can make a DFA, you can make an NFA. If you have an NFA, you can make a DFA. From an NFA, you can make a regex. From a DFA, it's exactly the same idea. So you can convert between any one of the three models here. And then you might think, well, what if, could it be the case that every language is regular? So if I give you any language, is it the case that you can always make a DFA for it or always make a regex for it? So we're going to try to settle that question today. So is every language L regular? And it may or may not be true. So so if I were to assert to you, I have this language L, and I tell you that it's not regular. Let's just say, for example, this language is not regular. What does that mean? There's no DFA for it. So would a proof be, oh, here's a DFA that doesn't work, here's a DFA that doesn't work, here's a DFA that doesn't work? Would that be a proof of that there's no DFA for it? No, of course not. So how would we actually prove that a language is not regular? If I tell you a language, how would you even prove that it's not regular? Well, we have to show no DFA works. So one way you can try to go about doing that is to say, every DFA has a different language than this one. This one I'm trying to prove non-regular. Every DFA in existence has a different language than this one, which would be enough, right? Because if there were a DFA for it, then that would have a language, that would have the same language. But if every DFA has a different language, then it can't possibly be. So the way that we're going to approach answering this question is kind of weird, but it'll actually lead us to that question of, or that statement of, all these DFAs have a different language than the target one that we want to show is not regular. So here's how we're going to do it. So let's let L be a regular language. So there is a DFA for it. I'm going to assert that. And let's let W be a string in L. So I'm just going to pick any old string in the language. I'll just assume it's non-empty, but it won't actually matter that much. So if from this W, what other strings are in L? So this is actually the way that we're going to approach the question. We're going to look at a string and then try to infer other strings that are in the language too, based off of this one string. And from that, we can actually get some kind of pattern that's repeating within the language, and that'll be the tool that will allow us to show that a certain language is not regular, because the patterns that we'll see in the regular language do not appear in the non-regular language that we're trying to show is not regular. So this will allow us to see a pattern that doesn't appear in some non-regular languages. Okay, so let's look at this language L. There's a DFA for it. And here's our infamous black box. And let's just say, for example, here's the start state. And just for sake of argument, let's just say there are two final states, but it doesn't actually matter. It could be that the start state's final two. It could be that there's only one state. There are many different ways of looking at this, but let's just say there are two. So remember when we were talking about if I have a string with n characters in it, how many states do I see? If I have n characters, how many states possibly repeating do I see? What was it? N plus 1, right. Let's just say there are n states in this thing. So this DFA has n states, of course. Now, what happens, or must happen at least, when I feed a string into this machine of length n or more? Yeah.
At some node, it must repeat itself.
It must see a state twice, at least. It could see the same state many times, but there's some state that appears twice when I feed this string through. I could feed a string longer than n characters. So it doesn't have to be exactly n. So let's look at a particular string of length n. So let's just say w is equal to w1 through wn, although we won't actually use those characters, just to say that it has n characters in it. Well, one of the states must repeat. It could be many states that repeat, but there's some state. It could be the start state. It could be one of the final states. But just for sake of argument, let's just say that it's just some random state out here. That's the one that repeats. Well, let's think about what happens. Well, the DFA says, I'm going to start in the start state. I'm going to read some characters, and then eventually we'll hit that repeating state. And then what happens at some point later? We hit that state, and then what happens at some point if we read more?
We will have to go back to that state.
Have to go back to that state at some point. And then let's just say that it's accepted, that it lands in one of the accept states. Well, that means that it goes to this repeating state, it does some stuff, it comes back to that state at some point, and then at some point later, once it's read everything else, it'll go to one of the final states. So if we look at what happens here, we have a bunch of, maybe 0, but some number of transitions that go to some state in the middle. Then some number of transitions that go back to that same state. And maybe it comes back to this state many times. We don't know necessarily. And then at some point later, it's going to read a bunch of transitions and land in one of the final states because we assumed that the string is accepted. Okay? Any confusion about that? So all of this follows from the pigeonhole principle because we have n characters at least, and there are only n states. So I'm going to actually name these strings that we are reading along each of these three parts. So from the start state to the repeating state, I'm going to call that x. Just the string from the start state to the middle state. Then I'm going to call the part that goes from the repeating state back to the same state. I'm going to call that y. And then the part that goes from the repeat state to the final state, I'm going to call that z. Okay? So what can you tell me about x, y, z? If I just put all three of those together, what can you tell me about that string? Yeah, it's being accepted. Why? Because if we just read the characters on x, then the y part, and then the z part, that lands in a final state, so it's in the language by definition. Well, that's the original string, so that's not really that novel or anything. Okay. What if I said, I'm going to delete the y part in the middle? So I'm going to only deal with xz and nothing else. Will that be accepted too? Yeah, because it would just be reading the beginning part, skipping the repeat part, and then just going straight to the final state. So that's in the language too. So what about this? What if I have a string with two y's in it? And the way that we're going to write this from now on is xy squared z. So the 2 upstairs means the number of copies of y. What can you tell me about that string? Yeah, that's in there too, because we could just go around the y loop twice. So that's an L2. Oh, what about x, y to the I, z for any I at least 0? Yeah, read the x part, do the loop. Sounds like a dance move. Do the loop I times, and then the z part takes you to the final state. So that's in the language too. Excellent. So could there be multiple ways of breaking up the original string w into x, y, z? Could there be multiple different repeat states along in this machine? Yeah, there could be. But as long as the string is long enough, then there must be some decomposition. There could be many, but there's at least one, I guarantee. Because we repeat a state by definition. Okay. What can we think about now? Well, let's look at this y part. So this y part right here. How short could that be? So could it be involving one transition? Yeah, possibly. Could it be 0 transitions? But think, it's a DFA. Do DFAs have epsilon transitions? No. So if we take a transition from a state to the same state, that must read a character. So what can we infer about y? The string that you read from the repeat state back to the same state. What do we know then? Yeah, it has length at least 1. So we can say, yeah, let me just write it over here. So the length of y is at least 1. And don't worry, we're gonna prove a result in a second that has all this written down anyway. Yeah. So the number of characters in y, which is the string that we get from the repeat state and just concatenate all of the transitions that you do until you get back to that same state. Because it's a DFA, we can't have epsilon transitions, so we must read something. So it has at least one character, but it could be one character. Other questions? So it actually, from these two parts that we have here, we're actually all ready to go, but we're going to actually do one more, which will make our lives substantially easier. So let's think about this. So what is the part in this XYZ thing which involves just going from the beginning until you hit that repeat state the second time? Well, what string do I get when I start at the beginning, go up, hit the state, and then come back to that same state? Just that part. Just X and Y. So let's see. Well, could it be that we will see a state twice, many times throughout the computation? In other words, could it be that I repeat this state and repeat this state and repeat this state and repeat this state? Could I do a lot of repetitions like that? Yeah, I could. So let's focus on the very first time that this occurs. So the very first repetition. Well, what happens here? Well, how early in the computation could that occur? In other words, what is the length of xy? Well, it can't be more than the number of states in this thing, right? Because it could be that we visit every state without repeating one, and then the very last one we repeat. It can't be any worse than that. So this tells us that the length of the xy string, which is going from the beginning, doing the loop part, is at most n, which is the number of states in this thing. So, and one more thing, just so that we're clear. We don't have to work with a string of exactly length n, but all that matters is that we have a string of length at least n. So as long as it's at least n, then we're okay. Any questions? Because the name of the result that we actually just proved by doing this will strike fear into your hearts for the next month. It strikes fear into the hearts of every computer science student in existence. 2 words, the pumping lemma. Okay? So you'll dread hearing those words from now on. But no, I'm kidding. But or at least I hope I'm kidding. So we actually just proved the pumping lemma for regular languages. So what is the result state? It's kind of long, so we'll just go one step at a time. So we're going to let L be a regular language, just like we did before. So that means there's a DFA for it, and we worked with it before. But in this statement, I'm not going to use the word DFA at all. So in our minds, we know there is a DFA, and the thing I'm going to say next relates to the DFA, but I'm not going to say the word DFA. So then there exists what is called pumping, if I can spell pumping constant P for L. And what does the P represent here? P represents the number of states in the DFA. That's all it refers to. So what did we need to do in order to do the analysis that we did before? Well, we needed to have a string in the language, but also what else did we need? So it was accepted by the DFA, but what did we need about the string in order for this to work?
I'm assuming the length of the string must be greater than P.
Exactly. So then we can only talk about strings that are in the language and have length at least P. So for all W in L with the length of W at least P, comma. Well then, those are all the strings that we care about. Well then, that tells us there is a way to break the string W up into X, Y, Z. There could be multiple ways of doing it, just like we discussed before. But there exists a decomposition W equals X, Y, Z, so that and then 3 conditions follow. Well, we derived 3 things before, and I say there are 3 things here. Do you think that's a coincidence? It's not a coincidence. The length of xy is at most p. The length of y is at least 1. And x, y to the I, z is in L for all I. At least 0. You made it. Ah. It's kind of a long statement, but this is actually all we'll need. So notice something interesting. Did I say non-regular anywhere throughout all of this discussion? So how do we show that a language is not regular? Did I just lead you down the beaten path for no reason? Or what can we do here? So this says if L is regular, then a bunch of stuff is true. But if something is wrong with the part after there exists, if there's something wrong there, then L cannot possibly be regular. It's the contrapositive of the statement, which is equivalent. So what do we need to do? Well, let's see. Well, what we can do is we can assume that L is regular to start off, and then try to work from there. So let's actually try to prove a language to not be regular. So let's look at this one.
Can I ask a question?
Yeah.
If I is 0, well, it's
Oh, yeah. I should have discussed that, yeah. So if I is equal to 0, that means we're going to take the string y 0 times. So this is something that students misunderstand quite a bit, so it's no issue. So the length of the string y is always at least 1, the length of the string. Though when we choose I equal to 0, we're choosing the string 0 times. So the string still exists, but it's just we don't choose it. In other words, for the DFA's perspective, we're not going around that loop. Yeah.
It's fair to say if I was 0 for x, y, I, z would be equivalent to xc.
Yeah, it's XC. Yeah. So whenever you have a string to the power 0, meaning you choose it 0 times, you just have the empty string for that part.
Just get clarification with the length of xy equals to p. How does it reach final state?
Oh, it doesn't have to be equal to p. So this says that, yeah, so if you go back to the DFA's perspective, the state that's the repeating state, that could be anywhere. So it could be the start state, it could be a final state. We don't know necessarily. So this is what is called an artist's conception. So it's not necessarily what it really would be in the real DFA. It's just that this is just what it looks like would happen. So it could be the final state. So yeah, if it were equal to P, then it would be a final state. Yeah. Other questions? Okay, so let's look at this language. So let's look at L equal to 0 to the n, 1 to the n, where n is at least 0. So this language will be pretty famous throughout the class. We'll see this one over and over in different contexts. Okay, so what does this mean? The strings in this language are some number of zeros and then the same number of ones. Crucially, the same number of ones. Well, if we tried to make a DFA work for this, then we read a bunch of zeros, but then how does the DFA remember to see the same number of ones at a later point? It seems hard for a DFA to do. So therefore, it can't be done by any DFA. Is that a proof? No, that just says it doesn't work. Well, actually, on your next homework, you're going to see a language where we have the same number of 0 ones and 1 zeros, and you're going to get a different answer. So just because the DFA can't count, that doesn't mean that it won't work. Okay, so let's actually try to formally prove that this is not a regular language, because it isn't. So how would you do this? So the result we will prove is L is not regular. The question is, of course, how do we do it? Well, the only thing that we really have at our disposal is the pumping lemma. But what does the pumping lemma say? It says that if you have a regular language, then these properties apply. Do we know that this language is L down here is regular? We don't. Also, that was a completely useless discussion on my part then. Sorry for leading you in the wrong direction. Or could we do something? What if we assumed it was regular? Then would we be able to apply the pumping lemma? Okay, let's try that. It might not work, but let's try it. Even though I'm writing the word proof here. So let's suppose, to the contrary, that L is regular. What is this type of argument again? If we try to prove something but we suppose the exact opposite? Proof by contradiction. Oh, okay. So that's why I put to the contrary there, even though you don't have to do that, it's helpful for the reader. So if L is regular by our supposition, what do we know?
The 3 stuff must be true.
Well, yeah, we'll back up. Well, what else do we know? There's a pumping constant P for L, right? So then there is a pumping constant P for L. Right? That's just applying the statement. Oh, one thing I forgot to mention before. You may think, where in the world did that word pumping come from? So look at the third statement down here where we have y to the iz. Putting another copy of y in, that's called pumping the string. So by putting more copies of y, we're pumping the string more and more and more. I mean, that won't be necessarily the terminology, but it's just where it comes from. Then, so we have this pumping constant P for L. Okay, great. So let's actually jump back up to the statement. It says, okay, there's this constant P for L, then for all W in the language with length of W at least P, then there's a decomposition that whatever. Well, if we were trying to show that this is not true, this is not the case with this. This says for every choice of W in L with length at least P, this holds. The decomposition part holds. If we were trying to show that this is not true, what do we have to do? Well, it says that every string works in the language with length at least P. But what do we have to do if we want to show it's false? Oh, sorry? So what we're looking at is this part right here. So the statement says that every single choice of W works.
That means you need to find one that doesn't.
Right. So if we find one string that's a counterexample, then this for all statement's not true anymore. Cool. So we need to pick a string in the language and have length at least P. Any suggestion? So we have to pick a string. Any guesses?
Maybe 0?
Well, if I pick 0, well, is that in the language? No. What if I pick 0, 1? That's in the language. What two properties have to hold of this string? Well, we have same number of zeros and ones, that's true. Well, let's go back up to the statement. It says, every string in the language and, what's that second part?
The string must be greater than the pumping constant.
Right, the length of the string has to be bigger than the pumping constant. Do I know if 0, 1's long enough? It might be. I have no idea. What is one way we can force it to be true? Yeah.
Have the n equal P?
Right, exactly. So if we pick the string 0 to the P, 1 to the P, that's guaranteed to be of length at least P and is in the language. Don't worry if you don't get this the first time. It takes a bit of getting used to this type of argument. So it is in the language and has length at least P. Cool. Any questions about that? Okay, so this is our potential counterexample. It might not work. Right? It might not possibly work, but let's just assume that it will. Then let's look at this part right here. It says there exists a decomposition into 3 parts. So for this string, 0 to the P, 1 to the P, there is a decomposition that works according to the statement. But if we're trying to show that there exists statement is false, what do we have to do? Well, we want to show that there exists is false. There's no decomposition that works. So what do we have to do? What we have to do is we have to show every decomposition cannot possibly work. Because if none of them work, this there exists statement is false. Cool. So we just need to break this string up into every possible way and check every single one of them. That seems quite a bit, right? Is there something about the X, Y, and Z that'll help us here? Is there something particularly about the X and Y part that restricts where each of the three could be?
Well, if we refer to our current language, X must contain a 0.
Must be in the zeros. The X part could be empty, but it's within the zeros, yes. What do we know about the Y's, though? Could the Y's contain ones? Could, like, the Y part bleed into the ones? No. Why can't it? Because right. So the Y part is only in the zeros. That's kind of nice. So how do we treat every decomposition then? Well, the X part has some number of zeros, maybe none at all. The Y part is only zeros, at least one of them by the second condition, and the Z is the rest of the string. So we're going to look at all decompositions. And here's how we're going to do it. It's going to be really easy. So the X part is going to be 0. I'm going to call it to the alpha. The Y part, I'm going to call 0 to the beta. And the Z part is the rest of the string. Well, if we write it all out, the Z part is 0 to the P minus alpha minus beta, 1 to the P. And the reason for that is the X and Y part only have zeros. There were P zeros to start with. Yeah, go ahead.
Could you go over why Y has to have P only in the zeros again?
Because of the first condition, which is XY has length at most P. Well, that's the prefix of the string, and I have P zeros at the front, so it must only be zeros. Well, for the Z part, we started with P zeros. The X part took away alpha of them. The Y part took beta away from them. So I have P minus alpha minus beta zeros left for the Z part, and all of the ones are left. Cool. So let's just reiterate. So the alpha corresponding to the X is at least 0, although we won't actually use that. It's just a good habit to think about this. But the length of Y, which is beta in this case, has to be at least 1. Because why? Because of the second condition. Cool. Okay, we're actually about 90% of the way there, believe it or not. But any questions up to this point? Okay, so, well, we are enforcing these two conditions, the first two. So the only one that really will give us the contradiction is the third one, right? So it says that no matter the number of Y's that you stick into the string, you will always stay in the language. Well, if we're trying to show that that's false, how do we show a for all statement to be false? Find one counterexample. Cool. So if we find one counterexample, that'll contradict everything all at once, which is nice. So let's do that. Let's do purple. So the original string has how many copies of Y in it? The original one. No. So how many copies of y are there? Well, the original string was x, y, z. So how many y's are in there? Oh, yeah, just one. So we better pick something other than 1. Because if we picked 1, we end up with the string back in the language. But that's not what we tried to prove. So it says it's true for all I at least 0. Well, what is one counterexample? Or like any choice other than 1?
P.
You could do p, but let's just do a concrete number. It'll be easier to see. Yeah.
0.
Yeah, 0 is fine. In fact, in this case, you can pick anything other than 1. But let's just pick I equal to 0. Observe the resulting string, and then try to show that it's not in the language. So that is saying, let's look at the string x, y to the 0, z. Well, that's the same discussion that we were talking about before, where y to the 0 is the empty string. So this is just xz. So no copies of y in there. And all I'm going to do is I'm just going to copy and paste the decomposition down. So the x part was 0 to the alpha, so the number of whatever number of zeros. And then the z part is 0 to the p minus alpha minus beta, 1 to the p. Okay, well, I have 2 runs of zeros here. Is there a way that we could just put them together and have one exponent upstairs? Yeah, so what cancels here?
The alpha and negative alpha.
Right, the alphas go away, but the minus beta is still alive here. So when the dust settles, we're going to have p minus beta zeros with p1s. So this is the string that we get. So now, if this string is not in the language, then we just proved, we just got a contradiction. Because it said it was true that it was in the language for every choice of I, but we found one if it doesn't. So for this string to be in the language, what has to be true? Yeah, so if x, y to the 0, z, the string that we got, is in L, then beta must be 0. Because if it's not 0, then we don't have the same number of zeros and ones. Okay? Wait, isn't that a contradiction? Yeah, because the statement said that it had to be at least 1, but we got that it's equal to 0. So this is a contradiction. And because we got a contradiction, therefore L is not regular. Any questions if that felt like a bit of magic at the end? So basically the property that we're looking at with regular languages is that they can repeat stuff at the beginning, quote unquote, the beginning of the string, but what is required of languages like this one is that you need to be able to repeat in 2 separate places of the string, in the zeros and the ones, in order for them to have the same number of zeros and ones. But because it only pumps at the beginning of the string, in some sense, then we can't pump the same corresponding part at the end, which means that we can obtain a string that is not in the language, and therefore any DFA for L must have a different language than this one, because it must accept a string that's not in here. Any questions about that? Okay, so let's do another one. So what would be an interesting one? So let's try this one. So slightly modified. So 0 to the n, 1 to the 2n, where n is at least 0. Well, let's see. I want to show that this seems not regular. Who thinks that this is regular? Who thinks it's not? No one thinks me. Okay. Yeah. So there's a dependence between the zeros and the ones here. So whenever you see some kind of dependence like that, it probably is not regular. And this is no exception. So is not regular. So how do we show that it is not regular? What tool do we have?
The thing we just did.
Yeah, the pumping lemma. Yeah, that whole argument. So, so what were the steps that we had to do? So what was the very first thing that we did? Assume it's regular. So it's basically just like one of the cool things about proofs like these is that they very often have some kind of logical progression that is the same every time. So you always assume that it's regular first. So that's the first thing. And then what was the second thing that we had to do? Yeah, there's that pumping constant. Yep. So I'm going to shorthand it, but exists a pumping constant P for L. Okay. So then what do we do after that?
Choose a string that's at least like P.
And length at least P and relation to L. In L. Yeah. So from experience teaching thousands of students in this class, the number one thing that students miss in the entire class is this part right here. Getting a string that is not in the language or is not long enough or both. So what are the two things that you always need to do at this stage? Pick a string in the language and it has to have length at least P. Okay? I swear, that's the thing that students miss the absolute most. If you can get that, good. You're on the right track. So we got to pick a string in this language with length at least P. So what's a good candidate for this? Yeah. Where's the P? Yeah, so just stick the, yeah. That's actually a good way to think about this. So most of the time, you can actually just stick the pumping constant P where the n is. And then that's the string that you use. Some languages, like the ones you'll see in your next homework, you don't have like the form 0 something 1 something. You just have like W in 0 1 stars such that W has, say, twice as many zeros as ones. So it's not in this specific form. I guess we're out of time, so I'll see you on Wednesday.